Alright, our final quantum mechanics chapter is chapter 13 from the textbook, and we're finally going to get to molecular structure, to looking at molecules that have multiple atoms and multiple electrons. So the first thing that we want to do as quantum chemists is think about the Hamiltonian. What's the Schrodinger equation going to look like? What is our operator going to look like? We're going to need, first of all, kinetic energy terms for each electron. So let's think of this starting out right now as CH4 for an illustration. Carbon has 6 total electrons. We're not just thinking about valence, but total electrons. And each hydrogen contributes 1. So there's 10 total electrons. That's 10 kinetic energy terms. And then the next question is, how many attraction potential energy terms are there going to be? Well, for each nucleus is going to be attracted to each electron. So it's a double sum where the capital N stands for the number of atoms. In CH4 case, that's 5. The lowercase n stands for the number of electrons. So in CH4 case, that's 10. So there's going to be 50 terms for CH4 that are attraction related. Each of the 10 electrons to each of the 5 nuclei, each of them depending on the distance between the electron and the nucleus. So that's what the RAI stands for, where I is referring to a particular electron and A is referring to a particular nucleus. Z is the charge on that nucleus. So for carbon, we'd be looking at 6, and for each of the hydrogens, we'd be looking at 1. Then the question is, how many repulsion terms are there? Well, the electrons are going to repel each other, and the nuclei are going to repel each other. And so we've got 2 double sums to deal with, and in each case we don't want to double count interactions. We want to avoid counting the interaction that is electron 1 to electron 1 or nucleus 1 to nucleus 1, and we also don't want to count electron 1 and electron 2 and electron 2 and electron 1 as separate forces. So that happens with this double sum here, where we only look at each electron as it deals with an electron with a number greater than it, and then the same thing for the nuclei. And these Z's are the charges on the nuclei. Capital R is distance between individual nuclei, and lowercase r is distance between each electron. And so the number of terms of electron-electron repulsion is going to be n, lowercase n, times n minus 1 over 2. And then the number of nuclear-nuclear repulsion terms is going to be n, capital N, times capital N minus 1 over 2. And so that's a very large number of terms. Think about if lowercase n is 10 for CH4, then that's 10 times 9, which is 90 over 2, which is 45. So 45 terms. And then the number of atoms is 5. So 5 times 4 is 20 over 2 is 10. So a lot of terms even for a small molecule. But once we've written out an entire Hamiltonian, it would take us a while to write out each of those terms. I won't ask you to do that for a large molecule. But the next question that comes up is, what do the wave functions look like for these molecules? And so let's think about how we would put this together. Let's think about, in this case, ethene, and just think about an individual carbon atom and what its sp2 hybridization is going to look like. Once the atom's orbitals are hybridized, instead of the electron configuration looking like 1s2, 2s2, 2px, and 2py, it's going to be 1s2, 2py will still have its electron, but then these 3 electrons are going to be hybridized over 3 orbitals that are each going to be sp2. So the new orbitals, each of those 3 orbitals, is going to be a hybrid orbital that's made from some linear combination of atomic orbitals. In this case, the 3 atomic orbitals in the linear combination are going to be the 2s, the 2px, and the 2pz on that carbon. So let's look at what the form of these 3 orbitals is going to be. We can start out with, like we said, it's going to be each of them is going to be a linear combination. We're going to assume, and this is not the case on ethene, but we're going to assume that the ligands, the 3 things attached to that carbon, are identical or close enough to identical that they won't affect the bond angles. And we're going to make these orbitals lie in the xz plane, since the py orbital is not contributing to the hybridization. I'm sorry, they're going to lie in the xz plane. And then so our goal is going to be to figure out what these C's could be. We've got 9 C's to figure out. Now, since the 2s is spherically symmetric, it's got to contribute the same amount to each of the 3 orbitals. So C2 and C5 and C8 all have to be equal to one another. And in order for normalization to be satisfied, C2 squared plus C5 squared plus C8 squared has to equal 1. Well, if they're all going to be equal to each other, then each of those C squareds has to be 1/3. And so they're each going to be either plus or minus the square root of 1/3. Now we're going to choose minus the square root of 1/3 because this orbital has the 2s orbital is negative out in the bonding region. Its sign is, and we want to make it positive so that we get constructive interference with the 1s orbitals from the hydrogens that come along that are also positive. And so we're going to use negative to make it a negative. So these are each going to be negative square root of 1/3. Now, if we make this orbital lie along the z-axis, then that can make our math a little bit easier because we can make C3 0. And so C1 is just going to, C1 is going to be whatever it needs to be for this to add up to, for C1 squared and C2 squared to add up to 1. And this will force a situation where C4 has to equal C7, and so that'll make the math a little bit easier, and C9 will equal negative C6, and so we'll take a look at that on the next slide. Alright, so here we are with what we know already. We've said that C6 and C9 are going to be equal in magnitude to one another. C4 and C7 are going to be equal to one another. So we've got a few less terms to deal with, a few less unknowns. But again, normalization is an issue. So C6 squared plus C6 squared has to equal 1. So that the px stays orbital. So that means that these are each, C6 is going to be 1 over the square root of 2. And that forces C1, because it has to be normalized in this direction, C1 has to be 2, the square root of 2/3. That way we have C1 squared would be 2/3. This one squared would be 1/3, and we'd get 1. And that forces each of the C4s to be square root of 1/6. And so we've just figured out what these hybridized orbitals are going to look like in terms of the atomic orbitals from which they are derived. Now an sp situation is going to be much simpler because the y and the x aren't hybridized, so they just remain as their separate orbitals. The 2s again has a negative sign on it, and it still has to be add up to 1 for the two hybridized orbitals, the square of their the square of their constants, of their coefficients, and so they have to be negative square root of 1 over 2. But since z is the only one hybridizing with it, and it has to normalize in this direction, their sign, they have to be square root of 1 over 2 as well. So the SP hybridization is a fairly simple situation. SP3 is a bit more complicated, so we're going to solve SP3 from two different viewpoints in the second video for this chapter. And then we'll deal with heteroligands with situations where the ligands aren't all the same in the third video.